Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RAW, and it is generously supported and sponsored by the Las Vegas Radio Amateur Club. Welcome to TennaTalk podcast number 3, called Getting Efficient. So let's take a look at today's agenda. We'll start by looking at the parts of an antenna system, and then we'll look at antenna impedance basics. We'll move on to some basic impedance matching techniques, and we'll look at what is SWR and exactly how it's calculated. Then we'll move into balance, ununs, and chokes, followed by antenna tuners, ground tuners, and then grounds, radials, and counterpoises. So let's get going. So here's a typical antenna. Look at the upper half of this. You'll see that that is the side of the coax that's on the rig side, and the lower half is on the antenna side of the coax or feed line. This is our rig, possibly with an internal ATU, that's why it's dotted, possibly with an internal BAL-UN or UNBALANCED here, which we'll of course talk about. This is an optional bias T in which you can inject DC into the coax, and the DC will ride along with the RF signal up to the antenna to power things at the antenna. Now here you have an optional current choke, which we'll talk about why you might want to have one here. But at the antenna end of the feed line, you definitely want to have a current choke pretty much all the time with a very few exceptions. And this is where you place your bias T to extract the DC to power your devices near the antenna. And again, you might have a BAL-UN type of a device here, along with your auto tuner and your antenna. Here we're looking at a vertical version of this antenna system with a tune whip and a counterpoise. And we'll see the usual familiar things up here, but the big difference is from the bias T, we can power not only an auto tuner to the whip portion of our vertical antenna, but a separate ground tuning circuit, which we'll talk about later on, to a counterpoise. And that'll help tune up and offset and balance this whole system very nicely. And I think we, in many cases, can improve the output of a vertical this way. So here we're looking at what sometimes is referred to as an infinite mirror. And this is a stack of partially reflective glass. Each interface will give us a reflection as well as some transmission. And with a ring of LEDs inside, you get this back and forth iterative effect of all the lights going down into infinity. And this is a little bit what your antenna system looks like when you're looking from the rig side out to the antenna. It is multiple interfaces. Looking at it like a stack of mirrors, we can think of them very much like that. Each interface is determined by the impedance match at that point. Each interface downstream multiplies the system losses, but fixing one does not fix interfaces downstream. And we must maximize the transparency at each interface to minimize the loss of the entire system. So one way to look at antenna systems and the transfer of power from the rig to the antenna to the radiated field is like a 10-speed bicycle, where our legs provide the power, the pedals provide a means of converting that power to rotary motion, the sprockets then connect with the chain to deliver that power back here to a different set of sprockets that turns the wheel that drives the bicycle forward. So let's look at how that might be interpreted in terms of antenna systems. Your legs could be the transmitter of the energy, like I said, your rig. Your pedals could be the feed line, could be considered that. You want 2 for proper energy balance. Your front gears would be the rig end tuner, the chain drive would be the feed line loss, The rear gears are the antenna and tuner, and ratchet is the reflected energy isolator to keep the energy from kicking back onto the pedals, back into your legs or transmitter. And so the behavior of a device like this would be the momentum that the bicyclist would get is a little bit like the electromagnetic radiated energy. The speed would be like the radiated frequency. Pedal pressure would translate to radiation resistance. Friction losses would translate to ohmic resistance. 1 foot of pedaling would be an unbalanced signal, and both feet pedaling would be a balanced signal. And if you drive only one wheel, it might be looking at it like a vertical. If you drive both wheels evenly, then you've got something that is more akin to a dipole. I know it may be a little bit silly or a little bit crude, but it's a way to look at the overall transfer of power at each step of the way. So let's take an example of this and look at the chain of losses here. So let's say we have a somewhat of a mismatch at the antenna of an SWR of 2.0. Not that unusual, especially not for things like off-center fed antennas and end feds. So that'll end up with about 11% loss right there. Let's say we have another 10% loss due to a sizable inductor and capacitor values inside of the auto tuner up at the antenna. And then with 50 feet of RG8X, we got another 11%, 8 to 12% loss. And then let's assume that our coax is a perfect match to the rig of 50 ohms to 50 ohms. We end up with this calculation ending up with about 70% transmission efficiency, losing almost 1/3 of our power before it even turns into electromagnetic radiation. Now, some people say ladder line is more efficient, but it is low loss, but it can change impedance when it's wet or when it's moved around by the wind near other metal objects like towers and masts and other metallic objects. So you have to keep that in mind. Now, I'll remind you of this slide we saw from TennaTalk number 1 that tries to put some perspective on SWR, which we're about to talk about. So everybody gets all worried about having an SWR close to 1.0. Well, that's ideal, but you can see an SWR of 1.5 is still only a 4% loss. An SWR of 2 is 11%. Even 3 is only 25% loss. Sure, it's appreciable, but it's not the end of the world. And your rig can easily handle that. So that's something to keep in mind, putting things in perspective and not getting overly uptight about your SWR alone. What you really want is energy radiated outward, or effective radiated power, ERP, you might see it shown as sometimes. So now, what is SWR all about? What's it really mean? So I have a nice animation here showing you what a wave looks like, electrically speaking now, on your antenna, or on your antenna system, I should say, at an interface. Might be your coax to the BAL-UN, might your BAL-UN to the antenna. Could be at a number of different places. If you have an impedance mismatch, some of that power is going to get reflected back, as we see here, and the rest of it's going to be transmitted on, like we see here. So a couple of the formulas that determine SWR, as a bit of a refresher, is that this thing called gamma is just a handy-dandy algebraic expression. It is the load impedance minus the characteristic impedance, typically your coax 50 ohms, over the sum of those two. And that's the same thing as the radiated power over the total power, including the ohmic power losses, to the 1/2 power, which is the square root. And the VSWR is calculated as 1 plus gamma, absolute value of gamma, so it just makes anything negative positive again, divided by 1 minus the absolute value of gamma. And gamma ranges from -1 to +1, from a perfect SWR match to a infinity SWR. So the efficiency is the radiation resistance divided by the total resistance, which is your radiation resistance and your ohmic losses here. So for example, an SWR of 2.0 can be seen when you have either an impedance, a load impedance of either 100 ohms or 25 ohms. They're still both 2 to 1 or 1 to 2 type of a ratio to 50 ohms. And that's how you get an SWR on either side of that 50 ohms. And 100 ohm would mean that you have an antenna that is probably longer than it needs to be, at least electrically. 25 ohms is when you're shortening that antenna, heading towards even lower ohmage, typical on a mobile whip, for example. So let's take a look now at coax loss. This is per 100 feet now. And we're plotting the frequency performance from 1 megahertz up to 300 megahertz for 4 different types of coax: RG58, 8X, LMR 240, and LMR 400, which you've probably heard about most of these. And you see that RG8X doesn't do too bad of a job from the 3 to 30 megahertz range of the HF band here. You get a 10 to 30% loss at 100 feet, which can be appreciable. But if you look at something like LMR 400, you got like less than a third of that, or third to half of that, 2.7 to 14. And it might be worth it if you've got runs of 100 feet or more, or if you don't have a lot of power to begin with, you're operating QRP, it might be worth investing in LMR 400, but it's considerably more expensive than 8X, and it's a lot thicker, heavier, and stiffer to deal with. So these are just some trade-offs to keep in mind when thinking about coax. So now let's take a look at impedance. This is the beginning of looking at what is really impedance, this Z or Z value that impedance is usually annotated by. It's the radiation resistance plus the reactance X with a J value here, which is the square root of -1. So that makes this an imaginary number. And as we'll see in future podcasts, it will be mapped out on a Smith chart in a rather useful, clever, but unusual way. So the radiation resistance, as we said, is just the real portion of the complex impedance. Values closer to 50 ohms requires less lossy inductor and capacitor values, of course, because you're trying to match closer to an SWR of 1. And the VSWR is derived from the ratio of R to the 50 ohm impedance. Either way, like we saw, 100 ohms or 25 ohms will still give you an SWR of 2.0. The reactance, or the JX term up here, is simply the imaginary part of the complex impedance. So the way we interpret this is a negative JX means that the antenna is electrically capacitive, which usually means it's electrically shorter than resonant. Maybe not physically, but electrically. And a positive JX value might mean that the antenna is generally inductive, and that means it's electrically longer than resonant. So you'll see this in the future videos. We'll be talking much more about complex reactance and complex impedance values and how to interpret them and how to compensate for them, how to deal with them, and how to dial them out completely. So now let's take a look at balanced versus unbalanced devices. Balanced devices by nature are things like dipoles, loops, and ladder lines. Unbalanced devices are verticals, end feds, off-center feds, things like the G5RV and coax cables. So now let's talk a little bit about impedance transformer ratios. And this leads up to what ratios we want to use in a BAL-UN or an UNBALANCED, for example. And it comes down to, I'll tell you the answer up front. The answer is that the impedance conversion ratio is the square of the turns ratio that the BAL-UN or UNBALANCED is wound with. So let's go through some simple algebra. So bear with me. You can review this later on over and over again to your heart's content to satisfy yourself that the math works out. But it is really quite elegant. So we remember from transformer theory that the ratio of the voltages is the same as the ratio of the turns. And side 1 is the primary, and we'll call side 2 the secondary. So N is the number of transformer turns, and we might remember that power is conserved across the transformer for an ideal transformer. And today, most transformers are pretty darn efficient, so we can assume that they're close to ideal. We can also remember Ohm's law, V equals IR, or I equals V over R. And we'll see this becomes very handy here in a moment. So if we calculate power as current times voltage, VI, we can replace the V over R in the I term and get V times V over R, and that's V squared over R. And the N in the denominator here in the subscript means either side 1 or side 2. Now we take this V squared over R. Well, that's the same as the V squared over R on either side, okay? Because it's true for either side of the equation. Because the power has to be the same. This is the power on side 1, and this is the power on side 2, and we set up here that power on side 1 and side 2, the primary and secondary, have to be the same. So that's what this part of it means. But if we do a little bit of algebraic rearrangement, we find that the ratio of the secondary to primary resistance is equal to the square of the secondary voltage divided by the square of the primary voltage. Very interesting. And so with a little bit of reassociation, we've got the square of the ratio of the voltages is equal to the square of the turns of the voltages, but that also is equal to the simple ratio of resistances. And for AC, resistance turns into impedance because we add a complex term, which we'll deal with in the future. And we get this nice equation of that the impedance ratio or transformation of impedance from 50 ohms up or down is equal to the square of the turns ratios up or down. And now let's see how that works. Let's talk about balance. No, not balloons, balance. So a 4-to-1 voltage balun, otherwise known as a Rutherford balun, you'll see it either way, is where we take an impedance that is balanced to something that is unbalanced. And we always refer to it from the antenna side to the source side. So that's why it's called a BAL-UN. And you'll see this because you'll notice that the center tap is right in the middle between two equal looking transformers. And that makes the system balanced on this side and unbalanced on this side. Also note that we like to use mixed 43 ferrites for balance. Now, no, not a none, but an unbalanced, unbalanced. This happens to be a 9-to-1. Now, notice something here. Remember we said that the turns ratio, the square of the turns ratio, will give us the impedance conversion ratio. So we see what looks like 3 equal size coils on the transformer here. And this is an auto transformer. It's self-transforming on a single ferrite. And indeed, this is 3 coils, and we're tapping across one coil in a place that is off center. It's not in the center, it's off center down here. So this is going to be unbalanced. And we see that from here to here is going to also be unbalanced. And it's a little hard to explain why it's unbalanced right now. We'll get to that in future videos. So we have 3 coils here, okay, compared to 1 coil here. So it's a 3-to-1 ratio of turns ratio. Square that, we get 9 to 1 for the unknown. This is why you'll almost always see BAL-UNs and unknowns as a squared number, whether that be 9, 16, 36, 49, 64, very common BAL-UNs and unknown ratios for just that reason. Because it's easier to wind BAL-UNs and unknowns in that way, in nice even ratios of 1, 2, 3 to 1. Okay, so what does this all do for us, right? A BAL-UN converts a balanced antenna to an unbalanced coax. An unknown converts an unbalanced antenna or load to an unbalanced coax. So we want to use the right ratio. There's nothing magical about ratios. We'd use a 1-on for loads that are about 50 ohms, like dipoles, okay? Loads that are 4 to 1, 200 ohms, which is 4 times 50, you'd use a 4 to 1 BAL-UN. That's like an off-center fed at 33% from the end. If we go further out and we off-center feed it at 25%, as we'll see here in a little while, to be able to accommodate more frequency bands, then we'll need to use a 9 to 1 BAL-UN, not a 4 to 1 BAL-UN. And if we want to go all the way to the end, like an end-fed half wave, that'll give us something on the order of 2,500 ohms, we'll need to use a 49 to 1 BAL-UN. And if you have something much higher, you might have to go to a 64 to 1 BAL-UN. But you'll be measuring the resistance, the radiation resistance on your device, your antenna analyzer, and from there, that's what you want to use, and that's what kind of BAL-UN or unknown you'll want to choose. Now, this also works the other way. You can go 1 to X, where X could be 4, 9, 36, 16, whatever, 49, for electrically short antennas such as whips, because those antennas will give you an R value much, much less than 50, and you'll need to boost that up as opposed to taking those down. So we reverse the sequence since, again, this is the antenna side, this is the coax side. Then we look at the ratio we need with an antenna analyzer, and we can put in the appropriate type of BAL-UN unknown. Now, you don't see many of those in actual practice because very often they'll compensate short antennas with a loading coil, which will do much of the work here. But a loading coil is essentially a form of a BAL-UN if you electrically look at it in just the right way. And again, the ratio is read from left to right, from the antenna side to the impedance side. And something interesting, that this ratio here is the same as the SWR, which is constant or flat across the entire HF band for which that BAL-UN or unknown was designed. And so a way to measure, which we'll see in the future, a way to measure BAL-UNs and unknowns is simply hooking it up in series between port 0 and port 1 on your nano VNA and looking at the SWR. And you'll see the SWR is 4 or 9 or 49. And that tells you immediately what the BAL-UN ratio is. Pretty simple, pretty slick, and it really does work. So let's move on. Okay, you may recall this chart from I think it was TennaTalk number 1. And again, this is a 40-meter half wave part of a dipole. Actually, excuse me, it's a half wave, and this is the center of the half wave. So this is a quarter wave over here, and this is a quarter wave of a 40-meter dipole. Okay, so this blue curve that we see right here, and we're looking at strictly at currents because that's what controls and generates our electromagnetic wave. That is the standing current wave for a 40-meter frequency wave on this 40-meter half wave dipole. And let's assume we're feeding it at the center with a 50 ohm coax right here, and it matches up pretty nicely. But if we try to operate this on other bands, for example, the next band we might want to operate this on is the brownish red that you'll see here, and you'll have 2 of these lobes. Whoops, we have a problem right here, right? We have 0 current. And that means we'll have very, very high voltage, which means voltage divided by current is impedance in the AC world. And that means this is going to be thousands of ohms, not 50 ohms. And we're going to have a terrible mismatch. We're not going to get any power into it. So guess what? That's why a natural center-fed 40-meter dipole does not work for 20 meters. Okay? Now let's take a look at 15 meters. That's the lime green curves. Okay, 1, 2, 3. Well, that's not too bad. And that's why you'll hear that a 40-meter half-wave dipole fed at the center can also work on 15 meters. And indeed it can. Why they say it's this third harmonic. And that's why not the second harmonic of 20 meters, but the third harmonic of 15 meters. But let's now go one further. Let's go to 10 meters, which is this purple curve right here, bouncing 1, 2, 3, and 4. And guess what? We have the same problem as 20 meters. The impedance, the current is very low, therefore the voltage is very high, and the impedance is very, very high. So we're not going to be able to operate on 10 meters with a center-fed half-wave 40-meter dipole. So what do? Give up? Heck no. We move our feed point. So let's say we move our feed point over here to somewhere in the 80% from the end point. Okay? Well then you might read something on the order of 200 ohms. And I've actually plotted the total height of these curves at different points to see the general sweetness of these load points, different places where we might place our feed point. These are the different sweetnesses. If we move it to 33% off the end, then I might be up at around 400, 450 ohms, okay? And you can see that it does pretty well for 10 meters and 15 meters, not quite so well for 20 meters, and not very well for the 40 meters, even less so for 40 meters. So some people actually move it down here to 20% off the end, 20, 22, 25%. You'll see that now. And they'll put like a 9-to-1 ratio BAL-UN there and be able to work all four bands on that same 40-meter half wavelength dipole, but it's FUD now 20, 22% from the end instead of at the middle. So that's what this is all about. That's how and why we use different feed points and why we use a BAL-UN or an UN in this case to feed this. And then, of course, this is the end-fed half wave. We'd feed it here. You'd see around well over a couple kilo ohms, K ohms, and you'll definitely want to have like a 49, if not a 64-to-1 ratio BAL-UN. And again, you can find this out by doing an analysis. But the interesting thing is why EFHWs work pretty well is everything comes together as about equally performing right here at the end. It all converges there. So it's kind of that's the magic point, and that's why EFHWs are what some people call the magic antenna. So let's move on. So here's an example of a retuning from the green line to the red curve of an end-fed half wave. You can see if we choose the right UN, and this one was moving from a 49-to-1 to a 64-to-1 UN for this particular example. And you say we got 10 meters here, and it got shifted over a little bit, yes, but still not too bad, still around 2 SWR of 2. And here we move from the green and to 15 meters, and now we have a very nice dip at 15 meters. Here we've shifted it over and we've dropped it down very nicely at 20 meters. And for 7 megahertz or 40 meters, we've shifted it over nicely from above 2 SWR to well below 2 of SWR. And so there's an example, and we'll actually do some of these live in upcoming videos showing you exactly how a tuner can do all kinds of magic tricks on adjusting the SWR by doing different impedance matching tricks. So let's look at chokes. No, not that kind of a choke. Current chokes. They're usually 1-to-1 ratio chokes and sometimes called guanella balance. Now, the term BAL-UN I don't like. It's kind of a misnomer because it confuses you from the function of a BAL-UN. A BAL-UN is really to change the ratio and convert from a balanced to unbalanced or to match an unbalanced to an unbalanced antenna. It's actually more appropriately called an RF isolator because it isolates the shield on your coax or feed line from becoming part of your antenna radiating system. Because if you don't, you could end up with RF in a shack. You could end up with all kinds of interference. Your SWR could shift around with your coax, getting closer or further away from metallic objects, all kinds of things. Your antenna, you don't want it to be part of the feed line and vice versa. You want to be isolated. So you put one of these suckers where the feed line meets the antenna, and you choke off the RF from coming down the outside of that shield, and that's called common mode current. Because remember, should normally have exactly the same amount of current going up the center conductor as you do coming back the braid on a coax, and you don't want extra current coming back down that braid. And that's what you usually find with common mode current. It's often driven by an imbalanced antenna or a bad match from your at the from your unbalanced coax to your unbalanced antenna. And the more unbalanced it is, then the more of a problem you've got. And you'll see now that this is horizontal in terms of the windings instead of vertical like a typical transformer. The coils are wound in series from the primary to the secondary on the hot side as on the neutral or ground or return side. And I want to point out that current thinking is to use mix 31 ferrites for current chokes instead of the mix 43 for BAL-UNs and UNONs. So using the choke, they can be snap-ons, they can be toroidal ferrites, or they can be even a coil of 6 turns of coax that's about 6 inches in diameter, and you may see some of those on the base of some vertical antenna kits that you can buy. They tell you to do that, and that's what it's for, is to become a poor man's choke. It's not as effective as using ferrites, not by a long shot. There are YouTubes on the internet to actually demonstrate this. We talked about using mix 31 for chokes. If you place it where the feed line meets the antenna, that keeps the coax shield from becoming part of the antenna system, and it prevents RF in the shack. Now, when would you want to place a choke at the rig end of your coax where the transmitter meets the feed line? Well, that reduces the pickup of local RFI into your receiver, believe it or not, by the outside of your coax shield. And you can also do that when you're using the coax shield deliberately to be part of your antenna system, when you're using it as the counterpoise on an end-fed half-wave antenna, using the coax braid as a counterpoise. And some people do that unwittingly, or they do that quite deliberately and put the choke at even a different location to change the length of that counterpoise. And it's a way of tuning that counterpoise, interestingly enough. So let's talk briefly about tuners. No, not that kind of tuner. This kind of tuner. This is a classic little Pi network tuner. Okay, both these two capacitors, one on the transmitter side of the inductor, one on the antenna side of the inductor, are shunt capacitors to ground, with the inductor in series on the hot side in between them. This is a little auto tuner. Up to 100 watts that you can purchase pretty inexpensively, works reasonably well. Or you can have a much more robust, wide range, higher power remote tuner that some people bury this in the ground. So it's weatherproof in a weatherproof box, but you do have to generally power this somehow, either through a bias T situation or through a separate power and control cable. So I'm not going to go into tuners too much on this podcast because we're going to spend a lot more time in future podcasts talking all about tuners, how they work, why they work, how to build them, how to adjust them, how to test them, and how to model them, which is really, really cool. So that's why I'm not going to spend a lot of time now. So the next thing I want to talk about are counterpoises. This is a very nice counterpoise. Grounds and radials. Not that kind of radial. You know what kind of radial I'm talking. So ground planes. It is not an AC house ground. Do not use your AC house ground for your ground planes. That could lead into some safety issues as well as not performing very well. And any RF could get back into your house and propagate all over your house and into your shack. This is coupled to the ground. So you have typically many wires on or in the soil. Very often they are cut to quarter wave for each band you want to operate on. And we can see here that you have a ground plane plate that has lots and lots and lots of radials. This is very traditional. Marconi was doing this back when radio was invented. So it's a very tried and true method, but it's not always practical. And it's pretty involved. So let's look at some alternatives. Well, one alternative is radial. So that's usually several wires, not dozens, but maybe 3 or 4 wires radiating out from the base. Again, they're often cut to quarter wavelengths of the desired bands, and they can be above the ground or near the ground level. But they're not grounds per se, they're radials, and they behave somewhat differently, but they can be tuned. And by drooping them down, you can actually raise the SWR of your vertical, which is typically short, and therefore it's typically going to be a lower than 50 ohms impedance. You can raise that, drive that impedance up towards, if not at 50 ohms, by drooping those verticals down about 40, 45 degrees. And that actually works pretty well. And that's why you'll often see radials droop down, especially on UHF VHF antennas. It works most effectively. Now, counterpoises are interesting because they're kind of the other half of a dipole, the missing half. So you're trying to create the missing half of a dipole without having it look like a dipole or up in the sky like a dipole. What it essentially does is it creates capacitance to balance the whip's impedance, or the radiating portion's impedance. So here you see a piece of coax, which is the braid. This is the center conductor of the coax. And, oh, excuse me, this is actually the coax feed line. This is the counterpoise, which is connected to the braid, okay? But and people actually do that. They actually they strip away a chunk of like 20, 30 feet of the coax, leave this to be the center conductor, and they use the braid as the counterpoise, and then they feed that as normal, and with an appropriate BAL-UN here. Actually, this is a little misnomer. This should be an UNON, quite honestly, if you want to do it right. So again, it's not connected to the earth, and it could be floating metal. It could be a lot of metallic things. A vehicle, metal furniture, uh, metal picnic table at the park, railings, metallic mat, or piece of screen. Let me show you what actually I use. I call this my eMoped Mobile QRP rig. So here's my telescopic vertical whip, 18 feet long, and my Xiegu 6100 running 5 watts, and I'm using the frame of this electric scooter as the counterpoise. And believe it or not, it really works. It gets out. I've worked DX with this routinely, and it's pretty amazing how effective it can be. So I encourage you to experiment with counterpoises. But we have a trick up our sleeves with respect to counterpoises, which actually helps and can help in some cases a lot. And that's called an artificial ground or ground tuner. So it's pretty simple. What they do is they have this little transformer here from a primary to a secondary for one reason alone, and that is to drive this meter over here. And that's with a variable sensitivity resistor, pickup resistor, to the secondary, to the current that's coming over being rectified by this rectifier, basically like a detector, okay? So it's a detector circuit that's got boosted in voltage because a few turns here, more turns here, like transformers. But where the work is done and the magic happens is in series an inductor selected by this set of switches and a variable capacitor. By turning this dial, we've got an air plate capacitor in here, somewhere on the order of 500 picofarad. And this will be somewhere on the order of about 20 microhenries, okay? With different taps at progressively less incremental. So it might be 11, 13, 15, 17, 21, something like that, okay? What this does is it helps you maximize the current to your counterpoise, okay? And whatever counterpoise you're using, if you use this meter to maximize your current while you're keying down with a CW key, for example, and you turn the switch and the knob, preferably not while you're transmitting, but when your key is up, and you make those changes and you key again, you're looking for maximizing the counterpoise current. When you do that, you're starting to balance your antenna system out. You're driving less current against your common mode choke, or worse yet, common mode down to the shack. And you have a much more balanced antenna and much more effective radiated power. And so this is one of the last things I want to tell you about today, because I think it's really cool. I have a big brother of this called the MFJ 934, and it's a combination antenna tuner and ground tuner in one. So it's a pretty handy dandy little box. Maybe not so little, but it's a handy dandy unit that lets me do a lot of experimentation and a lot of fun things on both the whip side and on the counterpoise side. And on that, I actually mounted a whip mount on the top of it, so I can literally use that as a base and hook up a counterpoise to a picnic table, set this on the picnic table, raise the telescopic antenna, and tune it up, and I'm on the air. Some takeaways. Most antenna systems have losses, and they can be fixed very often pretty easily and make appreciable improvements. We've also learned that expensive coax is not necessary and is justified maybe only for very long runs. We learned about balance on-ons and chokes and how to use them, and those are very important. In fact, they can probably be the biggest bang for the buck. In fact, they might even replace a remote antenna tuner by getting you within shooting range of the antenna tuner and SWR on the rig side. That will allow your rig side tuners to keep your rig happy, which is really the only function of a rig tuner that it's there for. It's not going to help make your antenna any more efficient. And we saw that a counterpoise tuner can help make your vertical whip more effective. And finally, there are many ways to create an effective ground, and I encourage you to experiment with that. I hope you enjoyed this podcast. The next podcast is going to go into more detail about impedance matching, tuning, and how balance work, and we'll talk about all about Smith charts. Don't get scared. I'm going to make Smith charts so easy, it'll be like reading a clock, an old-fashioned analog two-hand clock, not a digital clock. So with that, please click the like button and the bell icon and subscribe to be notified of future videos. I hope you enjoyed this. Please leave comments below. I want to hear back from you. What you liked, what you didn't like, what you want to see more of, what you'd like to see less of, and any topics for the future, anything like that, or your experiences. Love to hear what you've built. Love to hear what you've done with this information and what you have built with it, what you've experimented with, and the kinds of things that you learned and tricks you've found. Please share them with everybody. Love to hear it. And so until next time, this is Rudy, your antenna whisperer K7 RAW, saying 73 and have a great day. Bye-bye.